Well, we had a very interesting presentation from Stephen, who explained the importance of training, monitoring training intensity and the importance of having good feedback. He was really focusing on more from a physiological perspective. In my presentation, I'm going to focus on a more motor learning and mechanical perspective. And the aim of our project was to search for effective feedback variables to improve physical capacities of a rower and to improve their movement coordination in order to, in the long run, improve rowing performance. So, and although I think you all know what rowing is, I want to illustrate what I mean with rowing performance. And because we all like to watch rowing movies, mostly, I wanted to show you this race of the 2012 Olympics. Does anyone recognize it? Which race is it?
Lightweight men's 4?
Yes, the lightweight men's 4, the finals. This one was raced with 4 persons per boat, but it can also be 1, 2, or 8 rowers. And just the basics. It's actually the aim of rowing is pretty simple. You have to go as fast as possible from start to finish. But that means that rowing performance can be defined as the average boat velocity during a race. And what we also see is that rowers, as we all know, push off against water in order to move the boat. And this push-off requires a lot of physical strength, but also movement coordination, because you have to put in and out the blades of the water, and you have to coordinate your movements with the other rowers of the boat. And I've chosen to show you this race because it nicely addressed the importance of our project, because when the rowers cross the finish line, you can see that the difference between winning and losing medals can be very small. And sometimes they're really marginal. Maybe someone knows this race, 2016. And although these differences are marginal, the consequences of winning or losing a race can be emotionally pretty large, and financially sometimes as well. So this is the reason for coaches and rowers, of course, to try to optimize their training sessions. And one problem that is encountered, oh, I should forget a slide, is that there are actually quite a few objective feedback variables to monitor and improve individual rowing performance. So as we all know, as a coach, we cycle alongside the boat and we watch our rowers from a distance. And we do not only have to provide feedback on the performance of the whole boat, but we also have to provide feedback to the individual performance of the rowers. So our aim with this project was to help and support coaches and rowers by developing and evaluating feedback variables that can contribute to the improvement of rowers' physical capacities and movement coordinations in the long run rowing performance. So in order for feedback variables to be effective, they need to at least adhere to 3 criteria. So first of all, the feedback that is provided needs to be related to performance. So in this case, average boat velocity. Secondly, variables need to be accurately measured. And thirdly, rowers need to be able to change or adapt their behavior based on the feedback they get. So the first thing we did was to define key performance variables. And we made use of a so-called biophysical framework that actually states that a rower puts energy in the boat. And this energy can actually be defined as mechanical power output averaged over a stroke cycle. Most of this power output is used to overcome water drag and to create average boat velocity, our performance parameter. But, and now I really want to show you this movie because I just like it. What we can see is that not all the power is used to overcome water drag. But what's clearly seen here is that when the rowers push off from water, the water around the blade is moving as well. So things that move cost energy. And this energy or power output comes from the rower. And this movement of the waters does not directly contribute to average boat velocity. A second factor that where power gets lost to is that the boat, and it's not that easily seen here, but we know that the boat is not moving with a constant velocity. But during the stroke cycle, you have large velocity fluctuations. And these fluctuations will cost you exponentially more power output than you would have rowed with a constant velocity in order to reach your average speed. So to sum up, power output is needed to overcome water drag, but some of the power output that's delivered by the rower is lost due to velocity fluctuations of the boat and due to water movements around the blade. So the nice thing of this model is that it combines several parameters that are measured with the same SI units, namely watts. So that means if a rower changes one of the parameters, you can directly see how it affects the other parameters. Another nice thing is that those parameters are all strongly related to physical capacities and movement coordination. So in order to examine what parameters can be used as effective feedback variables, in rowing we focused on those three parameters. And we started with the power loss due to velocity fluctuations. Because we knew already beforehand that these parameters can be measured quite accurately, but we didn't know whether rowers were able to change their behavior or their power loss based on the feedback on this variable. So we did a feedback study, and unfortunately we found that rowers were not able to reduce their power loss when they received feedback on power loss due to velocity fluctuations. Then we looked at power loss, at variable power loss due to water movements around the blade. Therefore, there's not really a good method now to determine this parameter accurately. So we came up with a new method in which we instrumented an oar with several sensors, and those sensors should allow us to get a good estimate of the power loss due to the water movements around the blade. And we evaluated this measurement in the lab, and we found that this method is actually quite accurate in measuring this power loss. So the next step for now is to find out if you provide feedback on this power loss, if rowers are able to change this power loss and reduce it so that they can use more power output to overcome water drag. But the main focus of our project was actually the power output delivered by the rower and whether this power output can be used as a feedback variable. Because what Seiler already said, you can look at internal load, but external load is also important, and it's really important to understand if you measure the external load of a rower pretty well. Because nowadays we mostly look at stroke rate or boat velocity, but those parameters are influenced already by other factors, like number of rowers in the boat, for example, or the temperature of the water. So power output instead is a really good variable for external training load because it's strongly related to the energy the rower puts in the boat. So there are already methods that determine power output in practice. So the first step for us was to check or to evaluate whether the most commonly used method correctly calculates power output. So what the commonly used method does is actually it calculates or determines the force that a rower applies at the handle and the velocity of the handle. But now I'm going to ask you to do a little bit of a thought experiment to understand whether this method is correct or not. So you can close your eyes if you want, you don't need to. But imagine yourself in a very stable single scull on water. And you are in the middle of the water, but you don't have any oars. But you cannot fall off because the boat is really stable. And now you're going to move back and forward in the boat. What's going to happen is that the boat is also going to move back and forward, right?
Forward and back.
Forward and back. Sorry.
You're right.
But that means that you overcome water drag and you create velocity or speed. So that means that power output is dissipated by the water. But now we're going to measure our power output while not having any oars, and we will measure that we don't deliver any power output, right? Because we don't have any oars. So something goes wrong here. And using Newtonian mechanics, we found out what goes wrong. And that is that the commonly used method does not take into account that the boat has a non-constant velocity. And if you apply Newtonian mechanics, you can only do that if you have a frame of reference. So in this case, the boat that has a constant velocity or is just standing still. But we have a boat that is moving with a non-constant velocity. So that means that we actually have to correct our Newtonian mechanics calculations, and we have to add a fictive force. And this fictive force is related to the mass of the rower and the acceleration of the center of mass. And this one is also producing power output if you multiply it with the velocity of the boat. So in the next step, to conclude, the commonly used method is not determining power output correctly because it neglects that the boat has a non-constant velocity. And this neglection means that you need an extra power term that is related to the product of the mass of the rower, the acceleration of the rower, and the velocity of the boat. So in the next step, we wanted to quantify this extra term. So we did an on-water study in which we aimed to find out how big this term was and whether this term was affected by different rowers and different rowing conditions. So we applied force transducers in the oar on the rowing boat that can calculate or that can determine the force at the handle and the velocity of the handle. And we mounted sensors on rowers that can measure the acceleration of the rower. So we had a lot of sensors mounted on the boat and on the rower, and we asked then rowers to do to row with several trials. And during these trials, we instructed them to vary their force applied, their technique, and their stroke rate. So this was one of our rowers rowing the trials. You might recognize him or not, because it can be one of two. And what we found out of this after this study is that the commonly used method, because it forgets that the boat is moving with a non-constant velocity, underestimates rowers' power output with almost 12.5%. And the underestimation does not vary that much between rowers or rowing conditions. So on average, it will be 12.5%. So now we know how to correctly calculate power output. We wanted to know whether rowers, especially in crew boats, are also able to adjust their power output when they receive feedback on it. So we developed a feedback system that can be connected to the sensors of the boat we mounted in the first study. And we were able to provide feedback on power output using smartphones. Then we asked several crew boats to row 3 different training sessions. And during the training sessions, we asked them to row with their traditional feedback for the first 2 training sessions, which are stroke rate and boat velocity, mostly for the stroke rowers, and sometimes also heart rate for 1 or 2 rowers. Then in the third training session, we added power output feedback. And during all the training sessions, we asked rowers to comply with the prescribed training intensities of the coach. That were low intensity and medium to high intensity. The intensities what Silo was talking about. And we asked rowers to also give power output targets that are related to those training intensities. So rowers knew every training session what intensity they had to row and what power output target was related to that intensity. And what we found is that when the rowers did not receive power output feedback, so only the traditional feedback, is that the training intensity, the deviation from the target, was almost 25 watts. But if we provided rowers with power output feedback, we saw that this deviation decreased to 10 watts, or 8 or 9 actually. So that means that rowers are way better to comply with power output targets and thus training intensities when they receive feedback on power output compared to different feedback variables. So in conclusion, what we did in this project, we delivered a framework that allows us to define key performance variables in rowing, and we developed a feedback system that allows us to provide feedback on those variables to rowers. Using this framework and our feedback system, we concluded that power output can be used as a feedback variable to control training intensity, and thus in the long run, hopefully, rowing performance. And we found, unfortunately, that power loss due to velocity fluctuations is not effective as a feedback variable. The last finding is that we need to do more research to find out whether power loss due to water movements around the blade can be used as a feedback variable. That was it.
So thank you, Lotte, for a nice overview. This presentation is open for questions. Please state your name when asking questions.
Yeah, Marco Blauer.
Matthijs, maybe you can check if our coffee has arrived. It might be already.
I checked and it did arrive.
Oh, that's cool.
So, if I understand you correctly, the conclusion of it all is that measuring the power output is a good measurement to control training intensity. Is it a better way to control this than using heart rate, for example?
Well, it really depends on what you want to measure. So if it comes about external training load, so what you prescribe rowers, it's a better measure.
Yeah.
But if you want to know also what the effect is of prescribing that training intensity, or that external training, external load for the rower, how he or she affects on it, then you also need your heart rate.
Yeah.
So I would say you need to measure both to understand what's going on.
Yeah, because when I was listening to your talk, I was expecting it to be a measure of, the quality of the rowing technique or something like that. But then in your talk, you said, well, you need to train as much as you can in the green zone at a certain heart rate, for instance. But if you use power output to measure improved rowing technique, for instance, you are probably also going to deliver more power, and your heart rate will rise as well, and then you will actually be penalized for.
So I think the way to.
Did everyone hear the question?
So the way to decrease or increase your power output is actually fairly to or deliver more force or increase your stroke rate. So I don't want to say that power output is a really good measure to understand whether your movement coordination is improving. So I would say it's more a thing for training intensity than for movement coordination, although it's not totally excluded from each other.
Can I just throw in that obviously you would be interested in the relationship.
Yeah.
If technique improved and you could produce more power at the same heart rate, then that suggests you've achieved an efficiency improvement that's positive, but you need to know both to capture that.
Yeah. Yeah, makes sense.
More questions?
Niels Trigerius again. I was interested in your second point. You say that if you give them feedback on the velocity fluctuation, that they're not able to really adapt that, which goes against some of the literature on dynamical framework, where you say actually giving visual feedback is problem solving. So from that perspective, I was interested to hear if you focus on individual rowers, on single sculls, or was it on a team?
This study was on single sculls rowers. And the interesting thing is that I think coaches coach a lot on velocity fluctuations. So we asked rowers, rowers did training sessions in which they got feedback from the coach, like the traditional feedback, and then in other training sessions they got feedback from the system. And in both, with both kinds of feedback, the rowers did not reduce their power loss due to velocity fluctuations. And I'm not completely sure why that is. could also be that the our feedback we provided might have been, so it's quite complex to change your power loss due to velocity fluctuations because it involves your whole movement. So there's a lot of degrees of freedom you can change to change that power loss. And maybe this feedback or the movement to change this feedback might have been too complex for rowers.
Did you restrict any variables like stroke rate?
Yes, the stroke rate had to be 20
Yeah,
strokes per minute.
Down,
Yeah.
Which can impact your velocity of your body mass relative to the boat velocity.
Yeah, so if you increase or decrease it, that will influence power loss a lot. So that was why we asked them to row at 20 strokes per minute.
Yeah, okay. Yeah.
At what intensity?
Low intensity endurance.
I think it would be interesting to do the experiment with the rowers that are less experienced, because then if they get feedback, they will have probably more improvement than when you have rowers that are already at
Well, we had quite a range of skills. We had juniors, and we had people who are almost rowing at elite level. So the range was really big, and we didn't see. Well, we saw that 3 people changed their power loss, but that's not enough to say that feedback on power loss works.
There was a question in the back somewhere. First, I'm not sure who it was.
It was me, but I will skip it for tomorrow.
Okay.
Oh shit!
Lotte, how much room do you think there is for?
Wait.
Sure.
How much room do you think there is to adapt to those fluctuations? Because you cannot do without them in the end.
Yeah, so I think that's one of the. So there will always be power loss due to velocity fluctuation because you cannot row with a constant speed, except if you change your row or you go row anti-phase. I don't know how to say it in English. Okay. So I think there is not that much room to change, so that makes it also very difficult. And also when the feedback is based on the velocity of the boat, and this velocity is measured by a GPS, so there could also have a little bit of noise of the GPS in our feedback parameter, and that rowers could not detect real changes based on their behavior and changes that were due to noise.
Question in the back?
just as
Okay. Arjan?
Yeah, also a comment. I will address this question in a few minutes. What strikes me in your work is that power underestimation on the boat, determining power underestimation is 10%.
Sorry,
So
is
if 10% or more.
12,
If I
12.3.
understand correctly, if you would use a sliding rigger, you wouldn't have this underestimation in the calculation. Is that correct?
Well, if you aim to, if you have a sliding rigger and you aim to get a perfect constant velocity of the boat, then you don't need it. But you have to make sure that your boat is constant. Your boat velocity is constant.
Then I understand correctly.
Yeah.
So why aren't we doing that?
I think it was forbidden, right?
Then, okay, one last question. Sorry, one last question, if there is any.
These two. My question is, why should you aim to reduce velocity fluctuation? It's not. Nobody will ever avoid it, so it isn't.
So you can't avoid it, but we say from a reduce, but you have to reduce it because from this biomechanical point of view, there's this framework I show you. The idea is if you reduce the power loss due to velocity fluctuations, you can use it for overcome water drag and create average velocity.
Of course.